go through this entire thing with you so you have an idea of how to apply reverse engineering, you might say, or do the inverse problem from, usually they give you a density function, a Gaussian density function, the mean, standard deviation, and they ask you something about the probability of a certain event occurring. That's the usual. The inverse is they'll give you the probability of something occurring, and they want the standard deviation, the mean. So that kind of a problem, unless you do them, can mess you up. So I'm going to go ahead and do this. So I hope this thing comes to life. So let's just say this is x. It doesn't matter what it is. And this is a density function, f of x. And it has some mean, an unknown mean. And, you know, at the mean, it's going to be a maximum. It'll look like this. And f of x itself is 1 over the square root of 2 pi sigma, and it's exp to the minus the quantity x minus x bar squared over 2 sigma squared. That's the fundamental, that's basically the formula that tells you the general shape of this. And there are a couple of points I was trying to make last time. One is there's perfect symmetry about the mean on a Gaussian. Any kind of a normal distribution, bell curve, Gaussian distribution. At the mean, it's a maximum, and you know it's perfectly symmetric about that. And that's important. So if I say for this one, and this is a typical kind of problem I would ask, and I'd like to hear your thoughts on this. If I say that from point A, here, up, there's a probability, call it P1 of the event occurring. Maybe if I give hard numbers, it'll make a little more sense, okay? So say this probability is going to be 1/3, and you can let A equal to, say, 3. So I'm saying if it's above 3, you got about a 1 in 3 or 1/3 chance of the event being in that range at A or beyond A, X being there. And then if I say it's also got, say, call this B, let's say it has a probability of 1/4 at being less than or equal to B. Doesn't matter what A and B are. Maybe I'll make B, say, -1. All right? Everybody follow me on this? Now, the question is, and something I would ask, and I would expect you to be able to do this, is what is the standard deviation and what is the mean? Everybody got that? Now, what I'm going to say, and the way I would do this problem, your calculators may have an operation, an inverse operation that can get this directly, but I am not familiar with your calculators, so this is the one thing your calculators do have, and they have the ability, and I'll call this my phi, but I won't use x here, I'll use a different symbol, just call it y. And this is the normalized version of the bell curve. It's 1 over the square root of 2 pi, and then it's going to be exp to the minus y squared over 2. So it's a bell curve, but sigma and the mean have been gotten rid of. Here, though, y itself is related to x there. Y is x minus x mean over sigma. Can everybody follow me on this, class? Do you remember me talking about this? Now this, your calculators can do, and for this particular case in your calculators, when you're looking at this, here, the actual mean value is 0, and the standard deviation is 1. If you have your calculators, you might want to get this out and try this problem so you can work through it with me and make sure you've got a good handle on it. Now, you know, the problem I did in class had perfect symmetry. It was a third likely above, a third likely below a certain point. And I didn't realize it when I was looking at it, but if you know that for a fact because of symmetry, you could add up the lower and upper limit. It was 0 and 2, and divide by 2, and that will be the mean, guaranteed, because it's going to be dead center. because of arguments of symmetry. Follow me, class? This one's different. You all follow me? This one's got a little more complexity. But if you're going to do that, here's where your calculators can help me. I use MathCAD, or MATLAB has an inverse function for this. It's where I can get the value here if I give it a certain probability density. Actually, sorry, I did something wrong here. That's the probability density function. The value of y itself would be this. From minus, the value of this function is from minus infinity to y, and there would be a dy. Do you all follow me? It's basically the actual cumulative distribution function with sigma equal to 1 and the mean equal to 0. That's exactly what that is. Are you with me? Okay, so how would you go about doing that? I try to put this up on OneNote and make it clear, but I have a feeling, unless you really dug into it, you might not see it. There's one thing you know for sure, right? I know this, don't I? So I know if I look at this and I say phi here of y will be equal to something, and here's where I warn you about this. Remember, the way I've defined this function right here, it's not an integral from the lower limit to the upper limit. It's an integral from minus infinity to the actual point that you want the probability. Now, if it's 1/3 probable above, it's 2/3 probable below. Do you all follow me on this? I'm going to see this right here. Make sure you do. If you don't, ask, and I'll make it clear to you. But I want to see this with your calculators. So I'm going to say this is going to be 2/3. And now find the value of y for that. Remember, that's normalized. I'm using y instead of x because it becomes confusing.
I got 0.4307.
I want to see if that's right. I had 0.431 because I rounded it up. Anybody else get that? I want to make sure you all get that in your calculators. Because I'm convinced there will be mistakes made here. Did you get it? So I'll call it 0.4307, and I'm going to go with that, right? Now, here's the next part. And if you looked at this carefully, you know this, but I want to make absolutely certain because I messed up on a board. I was spending too much time trying to do a trick that didn't work. I know this value of y is equal to x minus x bar over sigma. Well, x, I know. That's a. Follow me on this, class? That's the hard limit, the real limit. A would be what I had there. So this is going to be 3. So it's 3 minus x bar, or u, whatever you want, over sigma. So now I have one equation with two unknowns. I don't know sigma and I don't know x bar. How many are with me so far on this one? All right. Now let's go to the other side. Remember, it's not symmetric, but what can I do? What am I going to do here? I'm going to evaluate this first and set it equal to 1/3, get the inverse of this. Do y'all follow me? That means sigma for this is 1 and the mean is 0. Follow me? So this is the function you're going to be doing the inverse of. With me? So when I do that, now I set phi, and here it's really of y equals, now this one is 1/4, right? Because I made it 1/4. What's the inverse of this? It should be negative, I think.
Negative 0.6745.
6745. Anybody confirm that?
Yes.
2, 4, 6, 8, 10, 12. We're missing. I don't know if 2 people dropped or not, but we have, my roster, we have 14, and I haven't looked at if anybody's dropped. But okay, now what is this going to be equal to, class?
-1 minus x bar over sigma.
Right. What he's doing is just saying, well, now for this one, right? I know that's the value of y, the normalized value, correct, class? That's equal to x minus x bar over sigma. Well, x itself is minus 1, right? And it's going to be that minus x bar over sigma. Y'all with me? Now, you guys can solve this any way you want, but I want you to solve it in class for me. And I want to do it because I am concerned that people, I'm telling you this on quizzes, you can't be too casual. You'll almost get relaxed. Oh, I made a sign here. Here's where you don't make sign errors because it messes up everything from here on out. If you mess this up, everything else is wrong. Now, so I'm trying to really encourage you to do it. Go ahead and solve that. I mean, obviously, it's 2 equations, 2 unknowns. How do you want to do it? Well, you can multiply by sigma here, right? And then you can divide by 0.4307, and then take that equation, stick it in there. But I want you to all do it just one time for me in class to prove to me that, in fact, you're capable of doing that math without any kind of, and you don't need to use your calculators to do simultaneous equations. Please just do it the normal way. Yes, sir.
On the quiz, would you be mad if we did like a matrix so I make it faster?
Yeah, well, yeah, you can. Yeah, it's a bit overkill, but sure, you can do that. Absolutely, you can do it. You really don't need to do it, though. If you look at this, right? Multiply by sigma. If you want to do it this way, multiply by sigma, right? And just take 3 to the other side, and multiply by minus. So you got x equals something. Put it in there. Then you got one equation with just sigma, solve for sigma, then solve for x. But I don't care how you do it. It's not hard. I just want to make sure you all can do it. Because sometimes the simple things would trip up people. Anybody get the answer? There's no wrong answers. I expect at least a couple of different answers, but what'd you get?
I got standard deviation is 3.619.
And I have something to say about that. You're probably right. What's the mean?
1.441.
Okay. That may be right, may be wrong. Anybody else?
I got the same thing.
You think I'm kidding about this, but this is where I almost am guessing I'll see mistakes. And I hate that because it should not have mistakes at this point. These should be automatics. I'd solve the equations, longhand and just do the final step on your calculator. Anybody else? I'm not trying to irritate you guys with this, but this is a little concerning to me because on the quizzes, I've noticed a lot of what I call stupid errors made with basic arithmetic. And I did have coffee today, and my shirt's not inside out, so. I guess some people don't have paper and pen, and so it makes it a little more difficult. Xander, what did you get?
I got 3.62 for standard deviation and 1.44 for.
Okay, so you agree. Anybody else? Did you get that? Okay. I'm expecting some people not to get it. Maybe you're redoing your calculation when you didn't get that. Did anybody not get it the first time? You didn't get the first time? I'm going to tell you, this will drive you nuts. These are the things that we're going to make sure we address so we don't have that problem. And they're trivial, and it's so easy to not be attentive. Did you figure out what you were doing wrong, by the way? And by the way, when you get these things, if you want to do a quick check, just solve that equation, see if it equals 0.4307. If it doesn't, you got a problem. What's that? Say it again. What did you say?
Oh, you're just.
I was wondering, I was paying, I was focusing, so I didn't hear what anybody said their answers were, but.
They're up there on the board. And I think that's right, by the way.
Hmm.
But there's one other thing I'm gonna do after everybody does this one time. Did you get it? Anybody? Michael, did you get it?
It's gonna get me there. I just gotta real quick.
Oh,
I'll just hold that for a second.
have you got it?
I'm off by like one.
This is the thing, I'm glad we're doing this, because this drives me nuts, because this is the stuff, I assume it's seamless, but that's the problem I have. Here's what I would do, solve. I'm just telling you what I do. I'll use this side right here, and I'm gonna just multiply by sigma. I'm gonna make this as easy as possible for you. So if I multiply by sigma right here, now I've got that, right? Then the only thing I'm going to do is take x to this side, or x bar to this side, and then I have 3 minus 0.4307 sigma here. And I come here, and I've solved for x bar, so now I have minus 0.6745 equal to minus 1 minus that. And actually what I'm going to do is this. Before I do anything more, I'm going to multiply everything by a minus sign to make my life easy. Sort of easy. With me? And then, now I'm going to multiply by sigma, and I get 0.6745 sigma is equal to 1 plus x bar. X bar is equal to 1 minus 0.6745 sigma. I'm sorry. It's going to be 1 minus 0.6745 sigma, and that x bar is over there is 3 minus 0.4307. Now, at this point, you're just gathering things. So if I want to, I can take 3 to this side, gonna get minus 2, and then I can take this to this side, and you're gonna get, let me do it this way, right here. And that should do it. That should do it. But I mean, you're just going ahead and reorienting stuff. Are you with me, class? You should get that as the right answer, but the way you always check it, and do this on the quiz, you get this kind of thing. After you get the values, put it back into one of the 2 equations. Make sure it agrees. All right, I assume we can move on from here. Got one more with this one before we move on. And I'm really making a point of this. All right, let me hear your thoughts on this part. And again, this is standard Gaussian. want to say this. I have a Gaussian curve. I don't know the mean. I bet you a lot of you will get this. But I do know some things about it. Listen carefully to what I'm about to say. I know I gotta say this carefully. From, say, A to B, I've got a probability, doesn't matter, say 2/3, okay? So I went from A to B. And then I have a probability from B upward. This probability I'll call equal to 1/6. You with me? All right, now how would you do that problem? You tell me.
I would do from B to infinity and then do from A to infinity, find the inverse of both.
He nailed it. What he's doing is he's not focusing on just this region. You could say this region, if you use the normalized thing, if you did this, what you could do is say, well, you take the limit at B and subtract from it the limit at A, follow me? And that would be the probability between A and B. Are you with me on this, class? And you would have to get two inverses right here, basically inverse it twice. With me? Then you might be able to do that. I haven't done that one. That may work. You may have enough information to get it for that one. And the reason I'm saying this is every time you do the inverse, you have a factor y that you solve for, and that's equal to, as far as the upper and lower limits, x minus x bar over sigma. So you would have two equations. One would be the upper limit, one would be the lower, and you could solve that. If I just had it from, if I gave it a probability from A to B. Are you with me? The problem with that is, and I know this intuitively, the mean itself, you can get like a 30% chance of an event occurring, say, a mean, or a 1/3 chance. And what I can do is I can move this way or this way and just arrange the width so that I always get that, and the mean itself wouldn't change. And that's the reason I'm a little suspect of that. So the way I just showed you, or you mentioned this, where you would go from, the integral from here on up has a certain value, and the integral from, or I should say, really, from here on down, you would subtract that from 1, and then from here on down has a value. That will nail it every time. That I do know. But I'm just mentioning these things because these problems aren't always going to be the same exact template. Things can change. Okay. All right, enough on that. And that problem in the book, was it 5-3? Yes, sir.
Does this work the same way, like if I went from like A to infinity instead of from negative infinity to A?
Well,
I know it doesn't work the same way, but can you solve it a similar way?
In your calculator, here's what I'm trying to do is focus on what you have available. Your calculators have a cumulative distribution function that start at minus infinity to a given point, right? And you know, if the cumulative distribution function, if you had the upper limit go to infinity, it is 1. It has to be, right? Because it is the integral of the density function. If you take the cumulative distribution function to any other point, it's everything at that point down to minus infinity. Now, I guess in your calculators, though, you do have the ability to start at a point A and end at a point B. So you could, in fact, you could do that, but you could use your cumulative distribution function with sigma equal to 1 and the mean equal to 0 to get the two values, or the inverse values. Oh, wait a second. No, there would only be one inverse for that. See, the minute you do a cumulative distribution function, lower and upper limit, you're only going to have the probability of it being between the lower and upper limit you don't actually have two evaluations at the upper and lower limit. What you'd want to do, and this is, I'm just telling you, with your calculators, always use the cumulative distribution function and assume it starts at minus infinity if you're doing an inverse, and take it to a point A. And that would be akin to the probability of the normal distribution function, normalized one that has sigma equal to 1 and the mean equal to 0. Then solve for the value. You're going to get, two equations and two unknowns if you have two different regions where the probability is known. I'm not saying that exactly the way I want to, but I hope you understand. Don't make sure you're getting everything from minus infinity to the point that you're at that probability. So whenever I say it's from like a certain point up to infinity is a third, don't use that. Use 2/3 from minus infinity to that point. Okay, enough said about that. Got a few things I want to cover now. I'm going to try to make these points clear. I'm going to talk about something when the event is very, very unlikely, and this is triggering. In the book, he talks about a situation where, and he uses the normal distribution, but he basically says that we've got a voltage, something like this. You got a voltage with a 1/2 volt offset, so this is V, and say this is 0.5 volts. And on here, you're going to superimpose noise, so you're basically going to have something like this. There's noise on here. And this is going to be for something, think of a gate operation where it's either on, it's going to have a certain voltage or in excess of it, or it's off. So this is assuming, you can assume this is akin to a 0 right here, as far as digital logic, but there's a voltage superimposed on it. And there's a threshold up here, and this threshold voltage is going to be 2.5 volts. And anything above 2.5 will be rendered a 1. Did anybody read this in the book, this part? This chapter? This is a legitimate problem. This is something where now we need the statistical information about this voltage right here. And in the book he says that this voltage that voltage actually is at 0.5 volts. So it's basically, if you did an averaging of all that noise, you would get 1/2 volt there. It's running at about 1/2 volt. And then he's going to give some information about this. Yeah, he's going to say the variance is actually equal to 0.2 volts squared. So the variance on this is going to be 0.2, which means the standard deviation is going to be equal to, for this one, it's going to be a square root of 0.2. So the next thing, and I want you to work through this with me, because it will help. If this is given, I give you the situation that I got a voltage, a DC voltage of 1/2 volt, and I got noise on it. And that noise has, the mean value of that noise is 1/2 volt. I'm saying it explicitly. But the thing has a statistical distribution where the standard, or I should say the variance is 0.2 volts. And they want the probability that this thing actually triggers. Do y'all follow me? So what do I mean by that? That the voltage goes above 2.5 volts. So it's smart to draw this first so you get kind of an idea of exactly what's going on. If this is the voltage, and this is the mean value, which is going to be 1/2 volt, that's the most likely value. And then you're going to have something like this, a bell curve, and way up here is 2.5 volts. Now, your calculators should be able to do this, but for there's going to come a point where if this gets too high, it won't be able to evaluate it. And I'll get to that in a second. But what you're really looking at is this. The likelihood that shaded area I've got there would be proportional to the actual probability of it exceeding that. Can you do this on your calculators? You should be able to do it. If you just take your cumulative distribution function and go from minus infinity to 2.5, find that value, and then subtract it from 1, right? That would be that probability. And the mean value would be 0.5. And again, this not the variance, what you would say is the standard deviation, the square root is 0.2. So if I was going to evaluate that, this probability, and I'll call it a triggering would be equal to 1 minus the integral from minus infinity to this upper limit, and this is going to be my y here, and y would be equal to x, which is 2.5 minus 0.5 over the square root of 0.2, and it would be of 1 over square root of 2 pi exp to the minus, and I might as well just go y squared over 2 dy. So what do you get for that?
0.00004.
0.000, one more?
Over there's 1, 2,
It's 5 zeros.
5 zeros, yeah.
454?
Mm-hmm.
Okay. I think that's right. The actual value for this is 3.81 or 3.878 times 10 to the minus 6. Is that what you got? So we're going to just say 3.875 times 10 to the minus 6. Very, very small chance. And I want to say one other thing. Whenever, see, this normalized value is like 4.3 here, something like that, if you actually take a look at it. When you go much above 5, the calculators can't do it accurately. Then you have to use, there's theorems that estimate that value. And one of them is it's the Mobier-Laplace theorem. I'm not going to hold you responsible for a lot of those things they're really at the, you might say, at the fringes of what you need to know. If you need to do something like that, you can look it up and you can see this. There's theorems that address that problem. But the chance of triggering is extremely small. Can you all follow me on this? Now here's the point I'm going to make. You're very small. Now, that's triggering for one, you might say, one event. All right, when you have ones and zeros, you did JK flip-flops and stuff like that, right? I mean, you've done digital logic. You know, whenever you have a logic gate, you got a clock, and there's a continual change in the input-output of any kind of clocking system. There's always a possibility of change. So a very legitimate question is, what would the likelihood of a false trigger? And in radar, this is the same setup. In radar, the possibility of a false alarm, given all the information, if you look at a target space, there is going to be a possibility that there's no target and you get an actual target. It looks like a target to the situation because of noise. That always happens. So you have to carefully do calculations. It should be very small. That's a very small probability. That's for, in radar, they call it a dwell. So when the radar is looking in that direction before it moves, that's a dwell. And there's a probability of getting a false alarm, the target not being there. You with me, class? Then the next time it comes, it looks, there's a possibility of a target not being there, but it's recording a target, basically false information. So if you look at the chance of the probability, if the probability is very low, you can do this. Of that happening, when there are n events, as n gets large, here's what you need to do. First, if that's the probability of false triggering, 1 minus that, or 1 minus 3.875 times 10 to the minus 6, I think you'll agree that's the probability of it not having a false alarm. Now, that's for one event. This is important. The probability of not having a false alarm for 2 events would be this squared. Do you all follow me on this? The probability of not having a false alarm for 3 events would be this cube. I'm making a point here. That's the probability of not having a false alarm for 3. Now, this value is less than 1. You all see this? And that's not having a false alarm. So I'm going to say this, and I've got a few things to say about this. If we just extrapolate that n times, that would be the probability if we do n events, n times that we have a possibility of a change in gate, but it doesn't change. That would be what happens, or with radar. If we look at that place n times, this is the probability of not having a false alarm. So the question is, what is the probability of having a false alarm? It's 1 minus this. So, or call it triggering. In the book, he calls it triggering. Probability of triggering. Right? Now that's a very small number, but as n gets larger and larger and larger, this eventually, as n goes to infinity, goes to 0, and you do have a probability of a false alarm or a triggering. Follow me? A good question, a typical mistake is this. Well, if this is the probability of a false alarm or a triggering in the first event, shouldn't the second event be that squared? No. You follow me? If you're looking at this, what happens is, and you know this instinctively, the likelihood of an event occurring, I mean, basically, or not occurring, the probability in this case of triggering, not occurring the first event, has to be less than the probability of not triggering the second event, because now you have 2 events. I'm saying this, I'm really struggling for the exact terminology, but I hope you see this. And because the probability is so very small, you could do Bernoulli, by the way, you could do the, the Bernoulli stuff with binomial coefficients. You could put that in there, but you'll never get it for large n. The thing fails. You can't, there's approximations. You can't do Bernoulli trial kind of things with this. But this is the way you would do it. When the probability is very low of an event happening, and you want the probability of that event happening over and over and over again, what you have to do is take 1 minus that to get the probability that it doesn't. I mean, basically everything's fine. And then you're going to have to take that to the nth power and subtract it from 1. That would be the probability of triggering it as it gets large. Now I want you to just work with me on this part, because here's where people fumble up the math on this one. If you look at this, and I'm going to say that. So I might say, with this equation, you with me on this one, class? Just going to use this equation, and suppose I asked you to solve this. I want to know how many events would occur if I had a probability to see if the probability of false triggering is 1% or 0.01. So I want to know what n is for this. Now I'm asking this because I always assume people can do this seamlessly. But I have concerns. How would you solve that? I think everybody knows. I mean, if you're going to solve this problem, let me just ask you this. This is the problem, right? Can everybody read that? Okay. So if I just look at this, and I'm going to multiply through by -1 first. Then I'm gonna take this minus 1 to that side, and I get 0.99, right? Y'all follow me on this, class? Then I can take, now this number right here is very close to 1, but it's not 1. Follow me? Now, how would you solve that? I mean, your calculators probably have a function to solve for any kind of equation, linear or nonlinear. But the way to do it with this kind of equation, anything you have something to a power, do a logarithm. It's always the easiest. So either natural log or log base 10, doesn't matter. So if I take the log of both sides, I'll do a natural log of this, and equals natural log of 0.99. Then the only thing I'm going to do is pull n out of there, right? Y'all agree with that? Now this one's doable on your calculators. Then you can say n, and tell me what you get, is natural log of 0.99 over the natural log of this crazy number, 1 minus 3.875 times 10 to the minus 6. And what do you get for that? Anybody?
2,593.
Anybody else?
What was your answer? 2,593.
You all get it? Now, here's my concern, and the reason I put, you get that? You get it? Okay. My concern is this. Some of you won't do the log, and you're going to get that first equation. And I promise you this much. You can't take a 1 over n root of things very easily on your calculators. In other words, I'm not saying this right. You can't do an iterative kind of solution with this very easily. So remember, logarithms are your friends with a problem like that. I'm really just underscoring that one little thing. But a lot of you probably have encountered problems like that already in some of your courses. But this is the kind of stuff you have to be aware of. You're going to get extremely small, extremely large numbers of probability. You have to have a way of, especially when you get things that are factorial to powers n, how to get the values. Okay, that's that problem. And remember, the triggering right here is a pretty good problem because it occurs so often in the real world. Okay, I'm not going to do the inverse of this, but not today, but I may go through this de Moivre-Laplace theorem where the binomial coefficients, really, if we use Bernoulli's Bernoulli trial kind of thing, when you get large values of n and k, you have to default to these approximate formulas. But we're not going to do that right now. Let's see. All right, next I want to talk about constant distributions and the standard deviation and the mean that are associated with them. And I'm doing this because it's necessary that you have a very good idea of this before we move into some of the stuff in quantization error. So if we have a density function, I'm just going to see if we have any of these markers that actually are harmonic functions. This one, maybe. No. If you take a look at this right here. Now, this is the kind of thing you have to be able to do. If I just give you something, if this is A and this is B and it's a drawing, and this was on the last quiz, I think. and I want the value here of this height, call it A. If that's a legitimate probability density function, how would you get that? It should be pretty obvious to everyone. Anyway. Well, what's the key? If you integrated that over the range of existence, you have to get a value of 1. This is a box, right? Width times height is area. The area has to be 1, right? If the width is b minus a, the height here has to be 1 over b minus a. Do you agree with that? That's a. It's that simple. Now, the next thing is, if you wanted the average value of that function, call it x, doesn't matter what you call it, but expected value of the random variable x, what would that be? We could prove it, but how many know, I'm not going to call on you, how many know what it is? The expected value, the average value. It's dead center. It would be a plus b over 2. It has to be. You can prove it by doing what? Taking the integral from a to b of 1 over b minus a, right, times x dx. Do you agree with this? And that'll get it. Has to. That's 1 over b minus a. And then you're going to have x squared over 2 evaluated from a to b. And you're going to get 1 over b minus a. And then it's going to be divided by 2. And you're going to get b squared minus a squared. And then you factor that b minus a, b plus a. Do y'all follow me? So you would do basically this. You'd have 1 over b plus a, or b minus a, pardon me. And then you would have 2 out here. And you would have b minus a, b plus a, and you can see the b minus a's go. So you have b plus a over 2, and that's the average value. But what I'm really trying to underscore is, one look at that, you know, this value, the mean, is simply a plus b over 2 by inspection. I'm trying to get that point. Now, the next thing is, what's the mean squared value, or what's the standard deviation? And this is going to be something you're going to have to remember. It's a constant density function. With me on this, class? For this one, if you wanted, let's get the expected value of x squared. So what are you going to do? Well, it's the integral from a to b. And it would be 1 over b minus a, because that's the weight a, right? Capital A. Then it's going to be x squared dx. That's 1 over b minus a. And then you're going to get a factor of 1/3. And then you're going to get the quantity b cubed minus a cubed here. Y'all agree with that? Now, factoring these things is not I don't have a great love for this, but you can go ahead and mess with that factor, and I'm going to get to the core issue here in a second, all right? If you look at that, since that's the expected value of x squared, you know that's equal to the value, if that's the expected value of x squared right there, let me do this. And I know that sigma squared is equal to x squared bar minus x bar squared. I can say the standard deviation is that, which is 1 over b minus a divided by 3. And then you're going to have the b cubed minus a cubed here, minus, and it's going to be b plus a squared over 4. Now, it's not looking real fun yet, but if you do this, because you got the b's and the a's in here, you're gonna multiply, you could get a common denominator, or if you, and that's probably the best way to do this. But when you mess around with this, at the end of the day, you're gonna see this whole thing comes down to, and the way he has it in the book is the easiest, it's gonna be 1/12, and he's gonna have it in terms of the b minus a. b minus a squared, and that is the standard deviation. That formula you should know. You can actually get it doing this. Messing with that, let me see a quick way. You would have to multiply this by b minus a here. You get sigma squared is equal to, and I would have 1 over b minus a, and then you would have b cubed minus a cubed over 3 minus b minus a times b plus a squared over 4. Then you multiply by 4 here. And multiply by 3 here. And divide by 12. I'm trying to show you this thing kind of quickly. If you do that now, this takes a while. But if you do this and you multiply this through, you're going to get a b cubed. Follow me on that, class? Because this is going to be b squared plus a squared plus 2ab. You're going to get a b squared times b is going to be a b cubed. It's got a minus 3, but there's a 4b cubed here. You're left with 1b cubed. Then if you look, it'll come down after everything's said and done. It's going to factor in a b squared plus a squared, and it's going to be minus 2ab. And that is that thing factored when you're done with it. But you'll keep on messing around. That's what comes out, but this is easy to remember right there. It's easy to see for a constant. And the thing about this is, the mean, just b plus a over 2 for a constant, and the standard deviation is just b minus a squared over 12. And those things you're going to use all the time. You'll see this later, but I wanted to put that out there for the constant distribution now, because some of the problems are going to require you to understand that and use it. Several of them, actually. All right, now, did you do that problem I gave you on the power equals I squared R and the density function for it? How many saw that on one? 1, 2. I gave that to you for a reason, because it's very pertinent to the kind of stuff you're going to get on the next quiz, and you should become familiar with it. So I'm going to do that problem. We'll come back, we'll use this for some things, but this becomes important. And your test is on Monday for EMAG, right?
Yes.
So you don't have 2 tests, or a quiz and a test on Friday. Then we'll get into, hoping to get into Rayleigh. Have you had to do mean standard deviation for any other course yet? Nothing. A lot of times with lab work, they would ask for that kind of information. But I don't know even what labs. You got a circuits lab? Did they ask for anything? Nothing statistical. All right. Well, for this one, the way, and by the way, what I'm showing you is very typical. What they're going to do is say that I have a resistor and that the actual power in the resistor is going to be equal to I squared R. That's standard basic DC. V, power is I squared R, V equals I times R. There's no, it doesn't matter what you do. Now they're going to say that the current itself has a Gaussian distribution. So call it Fi, or Fi of I. And it's going to be 1 over the square root of 2 pi sigma I, and by the way, I'm gonna make it real simple. We're gonna have a mean value of the current is zeros. That way it'll make it easy. And it'll be EXP, and here you're gonna have I squared over 2 sigma squared. That's the density function. I don't even need this I here. All the statistical information has to do with the current. With me? Now, the first question I'm going to ask, take a look at how this is defined, and this should ring bells. This looks like the y equals x squared problem, only with a scale factor of r. Follow me on this, class? The power is equal to I squared times r. Well, the r is a scale factor. It's a square thing. So now the first thing, I want the density function for the power. How do you do that? From last quiz we did this. You almost did the same problem, almost, without knowing it. Class? Well, the way, in this case, because it's a squared operator, right? When I look at this, the value of I here is going to be equal to the square root of the power over r, but it's plus or minus, so you have 2 roots. You know you're going to have 2 possible inverse density functions. With me, class? So now you're going to have f of I, and the argument here would be square root of p, or minus the square root of p over r, and then it's going to be plus fi, and it's going to be the square root of p over r. And then you're going to have, you can do it this way, take 1 over the derivative of the power with respect to the current. A lot of times I had derivative of I with respect to P, but 1 over that is still fine. Are you okay with this? Now, for this one, because it's a Gaussian function, you with me, class? For a Gaussian function, you know, especially we've got 0 mean here, we know it's symmetric. So f of I of minus a constant here is the same thing as f of I of plus a constant. How many see that and understand that? That means we can just double one of those. So now we're going to get 2 times, and I'll make it f of I of square root of p over r. And then I need to take the p, the I, and that's an absolute value. So that's going to be, this is going to be 2ir. So down here, you get 2I times r. And this would be fp, p. But anywhere there's going to be that prior variable, the I need to replace it with its equivalent p. Follow me, the power? That's all I'm going to do. So down here, the 2 go away, by the way. The 2's go away. And this is going to be equal to the square root of p over r. Since it's p over r and I got an r out front, I can just put square root of p times r. You agree, class? And at that point, now I can go ahead and substitute in and say that, well, my density function is that, and I just simply replace the I with square root of p over r, so it's going to be 1 over, it would be square root of 2 pi here, and I'll have exp of p minus p over 2 sigma squared r, and that whole thing is going to be divided by square root of p, and I can take the square root of r here, and that would be the density function. Do you agree, class? Everybody? So that's the density function. Then, I'm gonna ask you this too. If I wanted the mean value of the power, how would you get it? There's two ways. Y'all follow me on this one, class? So, what would that be? Here's a tip. You could, what? Take this, right here, this equation, and multiply it by p, right? And you would have a square root of p up top. And then you would integrate that from 0 to infinity, not minus infinity, because the power is strict positive. Agree, class? From 0 to infinity. And you'll get the right answer, but it's a lot of work, isn't it? Take a look at that. There's going to be some, you got an odd integral. It's doable, though. It is doable. But probably the easiest way to do is get the expected value of I squared r. Follow me? What is the expected value of I squared r? Well, what do you think? I squared r, that would be r times the expected value of I squared. Do you agree with that, class? And that's the mean squared value of I, right? So that's r times, and what is the mean squared value of I? I'll put it up here. Or I should say, minus you agree with that? This is the mean squared value, right? Minus the mean value squared is the variance or standard deviation squared, right? We have the standard deviation, or it was given in the actual density function. That would be known. Follow me? So what I can do is say, if I want this value, and what was the mean value of I? It's 0 by definition. There's nothing there. So if it's 0 by definition, this is just going to be sigma I squared. That's straightforward. And that avoids this integration. You can do that integration. I mean, it is actually a solvable integration, but it's kind of a pain. Yeah.
Where did you get square root of p times r at on
All right,
the?
take a look at this for a second. Do you agree power is I squared r?
Yes, sir.
All right, now solve for I. Well, you take p over r and then take square root, but you'd have plus or minus the square. That's very good.
I'm talking about the denominator on the BCF right there.
All right, do you recognize how we got this?
Yes, sir.
All right, what is dp di? Come over here. Take a derivative of p with respect to I. 2 ir. And there was a 2 here and a 2 here, and I erased it. That's how I got it. It's only just going through the motions, taking derivatives, replacing, or putting the derivatives where they belong in the equation. Yes?
Where did the square root come from then?
Of which one?
The
This?
P, yeah, the P.
Well,
Your
if you're looking-
derivative is 2
So, what's it? Are you talking specifically about this?
Yeah, and then denominator.
All right. What it was what? First up here, we had a 2, right?
Right.
And then we had to take derivative p with respect to r, right?
Right.
Follow me on this. So derivative p with respect to r is going to be 2ir, right? Now I have to, can I get rid of the 2's? Okay, get rid of the 2's. Now what is I? All right, so I is equal to square root of p over r. And you can see I got a square root of r down here and an r here, so that's really just square root of r, isn't it? And I brought it right in here. So I made it square root of PR. And then I factored out the R there, because it's a constant. And that would be the density function. Now you can, and I'm saying this, if you look at this, that's the thing you're actually going to integrate when you multiply by p. But when I multiply this thing I circled by p, I'm going to have a square root of p times e to the minus p 2 sigma squared r. That you can do by parts. It's a bit of a pain, but you can do it. Okay. All right. Let me finish this last thing. So the final thing I want to talk about, this is the Rayleigh distribution. There's the Rayleigh and the Maxwell-Boltzmann, but the Rayleigh is really important, and I'll show you why. Hopefully, I can make it clear to you. And I believe Lord Rayleigh came up with this, but it's a targeting algorithm, believe it or not, or it had to do with statistics of targets. So if you have two variables, x and y, and they're orthogonal, like on a map, a two-dimensional grid, and assume that they both have Gaussian distributions, so both of these have Gaussian distributions. And sigma of x is equal to sigma of y. This is important. And assume there's zero mean. Now, they don't have to be, but it's a lot easier to do this. Now, here's what what these statistics do. If you think about this, and then I create a new variable, call it r, that's equal to the square root of x squared plus y squared. So this has to do with a bullseye on a target. If this is x and this is y, and the grid is centered, dead center in a bullseye, then if you look, the distance r here is the square root of x squared plus y squared. You follow me on this, class? And if you wanted the probability of something shot at the target being in that area there, so it's dr thick at a radius of r, the statistics I'm about to show you, or the distribution, describe that. So now, first thing I have to do is say, well, what is the density function? Well, f of r here, and in his book, this is the next section, section 6. His book shows this. I'm going to use the exact form he has. This is r over sigma, but I have something to tell you. Make sure you get this right. This sigma is either sigma x or sigma y. It is not the variance of r. In other words, that value of sigma squared is the variance associated with the x and y statistics. And you could think about this, that if, you have x statistics, they would be Gaussian. If you think about this, we would have a Gaussian distribution just in x. Forget about y. Then in y, we have a Gaussian distribution. Same mean, same average value. If you look at the statistics, or I should say the density function for r, now you're going to get what I'm about to put up here. And this is going to be exp to the minus r squared over 2 sigma squared. And I want to make a note, this also has to do with the x or y standard or variance or standard deviation. Follow me? There's a different value for r, but they never use it. They just use the x and y r values for variance and standard deviation. Now, the nice thing is, when you want the probability that r is, and it has to be greater than or equal to 0, you can't have a negative value, and less than some value small r, this means that large r is a random variable. It's from 0 to r. that's equal to the integral of r, and then multiply by r, so you're really gonna get r squared over sigma squared exp to the minus r squared over 2 sigma squared dr. This will go from 0 to small r. And that happens to be equal to 1 minus, and this is the nice part about this I like, just minus r squared over 2 sigma squared. So, and you can do this integral straightforward. The way that they normally do it is if you look at this and you let x be equal to exp of minus r squared, actually, what am I doing? This should be an r, not an r squared. This is just r, my bad. Because there's an r there. So when you integrate that, that's what it'll come out to. And you let, I mean, you really say that there's going to be a variable of, you just call it like u equal to e to the minus r squared over 2 sigma squared. Take a derivative of that. Then you're going to get minus 2 times r out in front. And you'll have that exponential, and you can do the integration backwards. Let me just finish up here. So that's the probability. Now, the nice thing about this probability is this is trivial. I don't need tables. I don't need to do an inverse function to get values forward or backward on this, right? So the typical problem with Rayleigh, and I'm going to do this hopefully, if you actually look, I'll talk more about the mean value and the actual standard deviation of the Rayleigh thing, but there's an example in the book, or in the PDF I gave you. By the way, these are on page 80 through 82. But if you look at the example, exercise 6.2, matter of fact, I'm going to put this up here. We'll be done as soon as I get done with this. This is not hard, but remember, this thing has to do with targeting, and it will make a lot of sense. And it is accurate, too. There's a slight skew in the vertical because bullets do drop and stuff like this because of gravity, but it's pretty close. If you look at that example, they say that I have a target, and the diameter of the target is it 10 inches?
10 inches.
10 inches?
Yep.
10 inches. And they have, now, is it standard deviation or variance they give?
Average miss distance.
Oh, okay. So this is the problem. So they give the average miss distance of what?
2 inches.
So 2 inches. I didn't get to this, but 2 inches is actually going to be equal to the square root of pi over 2 times sigma. And hold on. I didn't put this down, but there's 2 things I should put down. When you actually look at the mean value of a Rayleigh, it's equal to the square root of pi over 2 times the standard deviation, but this is the standard deviation of either x or y. And then the actual mean squared value of that is just 2 sigma squared. Okay. Now, I didn't get to that, but these formulas work. I believe he works these out. You can get these things just using that distribution right there and solving the integrations. Right? It's not hard to do that. But the nice thing is, these things are very simple to evaluate, trivial. So he gives you an average miss distance of 2 inches, right? Therefore, we can get sigma. Take a look at that. Sigma would be equal to 2, right, times square root of 2 over pi. Now we have sigma. Follow me? Now, after that, he asks a question.
What's the probability that they'll miss the target completely?
You hear that? So the probability he's going to miss the target completely. So if it's a 10-inch diameter, the maximum radius here is going to be 5 inches, right? So R, 5 inches. What he wants is the probability you're going to miss it completely. Now over here, this is the probability the arrow will be from 0 to R. Follow me? Well, 1 minus that would be the probability it's not there or that it misses. Do you agree with that, class? So if I take a look at this, that means the probability of a miss is actually going to be 1 minus EXP to the minus, and in this case, R is 5 inches, so greater than 5 inches, and it's squared over 2 sigma squared. I'm just stating the obvious with replacing the R with 5. I didn't put the sigma in yet, so this is really going to be just EXP to the minus 25 over 2, and then sigma squared, if you look at this, and you square it, you're going to get sigma is equal to 4 times 2 over pi. And that would be sigma squared. So you come over here and divide that by 4 times 2 over pi. And what do you get? If you don't mind me, if you don't mind, tell me. Here's where you can make mistakes, not getting this direct, because that's a sigma squared in there. And that is that sigma that I'm using there. Anytime you see sigma at these things, the symbol sigma, that is the variance or standard deviation of the X or Y event. What'd you get?
I got 5.44 times 10 to the negative 5.
That doesn't sound right. I think I get 0.07, but I'm not sure.
Is it point?
Oh, hold on, I didn't do-
0.0074.
Yeah, that's what I got.
Okay.
Anybody else? Here's where you typically make mistakes, going from here to here. I'm telling you that. Did you get the right answer?
Yeah, I didn't do the times 2 on the bottom down there. So I did like,
Oh.
yeah.
And now, make sure you can do those calculations. A logical thing is what's on the quiz on Friday. I'm going to have stuff from the Rayleigh distribution you're going to solve, and we'll do some in class. And there'll be things that we just talked about from before. All right, so it's basically the last 3 lectures all kind of rolled into one. And the problems are going to be out of section 2, 6, and I didn't have a chance to get into quantization error and all that, but if I have time on Friday, I will. I want to make sure we get through this stuff because it is important. Now that's targeting, and that's actually kind of important for a lot of things, but it's statistics involved with actually real targeting kind of things. The only other one we need to do that's really important with respect to natural phenomena is the Maxwell-Boltzmann distribution. I'm not going to test you on the Maxwell-Boltzmann in a direct sense. I would give you the density function, might ask you a few things about it, but you at least need to be aware of it. Okay, thank you. I hope today's lecture was okay. Today I